your chapters for the final project. We'll review them and send them back with comments, and then we're also going to set up 2 sets of meeting times where we meet with the groups to discuss how things are going, and then another meeting where we discuss the feedback that we sent back to you from your rough drafts. And we will also discuss that in discussion section on Wednesday. So the list of instructions will be posted on B courses on Wednesday, and we'll discuss it in discussion section on Wednesday. Any questions?
When is the final paper and presentation?
The final paper and presentation are due on the 13th.
13th, the first day of the final.
Oh, okay.
Yeah.
Oh, okay.
And they'll provide some points that we think you should include in your individual chapters.
Great.
Okay, any questions about that?
Okay.
Yeah, what do you, Professor River? Eric's got a lead.
Oh, okay. Great. So, okay, coming down the home stretch here, we'll have, I guess, 3 more guest lecturers in this course here. Because we're having Cheryl Hurani from Sandia on
Monday.
Monday. We'll have Kim Boudil, recently appointed as Principal Associate Director for Business and Complex Integration, formerly VP for the labs at UCOP. And she'll be talking with us on the 22nd of April. We'll do the crisis simulation on
The 24th.
24th. Good. Okay. Today I'm very privileged here to have a colleague of mine from my years of Livermore here with us, talking about how do we know, how do we monitor for compliance, for testing, pre-verification. William Walter is a research geophysicist at Livermore National Laboratory, where he leads the geophysical monitoring programs. He also serves as the chief scientist for the source physics experiments, phase 2 dry alluvium geology chemical explosions planned to commence this spring. In 2018, he was elected to a second 3-year term on the board of directors of the Seismological Society of America. He's also currently serving a 3-year term in the National Academy of Sciences Committee on Seismology and Geodynamics. He served on the seismic subcommittee for the National Academy of Sciences panel that issued a 2012 report updating the technical issues relating to the Comprehensive Nuclear Test Ban Treaty, the CTBT. In graduate school, he collected seismic data from U.S. nuclear tests in Nevada and from the 1988 Soviet Joint Verification Experiment, the JVE, in what is now Kazakhstan. We have a student here from Kazakhstan. He is a co-author and author of more than 75 peer-reviewed scientific papers. His research areas include geophysics, technology, seismic source physics, earth structure, tectonics, pre-verification, and related policy issues. Bill received his BA from Physics, Middlebury College in 1984, and MS in Physics and from UC San Diego in 1986, and a PhD in Geophysics from the University of Nevada in 1991. After working at Livermore for 2 summers while in graduate school, he joined Livermore as a postdoc in 1991. So without further ado, we're going to have a fascinating lecture today. Take it away, Bill.
Thank
Thank you very much for your kind invitation to come and talk to you today. And I'd like to keep it very informal, so as you have questions, please raise your hand or wave or just yell out. That's fine. Or if I start to speak in jargon, which I kind of fancy to do, stop me and say, what the heck do those letters mean? And we can have a good discussion. I had a lot of fun putting this talk together. There's a lot of history to talk about with nuclear testing. We're coming up on the 74th anniversary of the first nuclear test back in the very end of World War II. There's a lot of interesting stuff to talk about, so I'll kind of go through this some detail here. But let's start with the basics. Who here has felt an earthquake? I think that most of you, right? So you're familiar with that feeling, funny feeling where the ground feels unstable and it's moving. It's moving up and down. We can trace it out with a typical sort of seismogram here, where we've got the velocity of the ground in this direction and time in that direction. And if the ground is moving very much, we have low amplitudes, and if it's moving a lot, we have big amplitudes. This is an actual nuclear test, one of the last large nuclear tests at the Nevada test site, recorded at a station in the Sierra Foothills, Columbia, at Berkeley, seismic stations runs. And for comparison, here's an earthquake that happened similar size, about 5.5, at the embedded test site back in 1992. And you can see, it's different. The character is different. You can see there's sort of more of this low frequency, so more slowly going up and down stuff here, less of it up here, more of this stuff near the beginning, less of it here. So there are ways to use that information of how the ground moves to identify an explosion with pretty high confidence, it turns out. I hope to convince you that. But I'm showing you this. This is the textbook classroom way to do it. Here's the way you might really face it, right? You're an operational officer working on treaty monitoring, and you're facing incoming seismograms, what's happening, and you see this, two events, one of which is an earthquake and one of which is an explosion. How do you tell? Pretty tough, actually, right? The Earth is filtering this in a way that makes the two events look extremely similar. So this is the reason why this has been such a problem. If we had this case, nuclear mine would have been solved 50, 60 years ago. I wouldn't be here talking, it would be a done deal. It would be great. But this is the hard problem we have to deal with. And so there's been a huge amount of investment in R&D to figure out why does this happen, how do we fix it, and how do we identify events very robustly. So I'm going to come back to that. So we'll start off with kind of history and the treaties. And the treaties are very tied to what our monitoring capabilities are. And then we'll go into the more technical stuff at the end. I'll show you how you can separate those two and really pull one out as an explosion pretty straightforwardly after you do your calibration. So there's been a lot of nuclear tests over the years. Here's a histogram by country from the first tests at the end of World War II through the last nuclear test, which was North Korea in 2017, too long ago. You can see this big peak during the height of the Cold War. Very interesting gap we'll talk about in 59 and 60, when there was a moratorium. You can see kind of this tailing off here. We'll talk about that too after the conflict testing treaty stuff. Interesting too is where these tests were. They're all over the world. I think a lot of people don't really realize how widespread nuclear testing was. This is atmospheric nuclear tests. Last one was in 1980. We'll talk about that, but they're all over the place, including the oceans. Up here. Here's U.S. testing grounds in Bikini. And then here's a full suite. I couldn't find a good map of just the underground ones, but the underground ones are the open circles. So here are some large ones that the U.S. did in Alaska in the 70s. You can see, for example, the former Soviet Union did these ones all over their country. They had so-called peaceful nuclear explosions. They actually used them to prospect for structure of the Earth. They tried to stimulate oil and gas. Actually, the U.S. did that too. There was creation of cavities for storage of gas. All kinds of, there's a lot of enthusiasm in the 60s and 70s for trying to use nuclear testing. Do work, create cavities, dig canals, do things that would be potentially useful. But that turned out not to pan out too well. But there was a lot of enthusiasm today, and that led to some of these tests. But you can see it's pretty much everywhere, only South America and Antarctica, places that we haven't had nuclear tests. Go back and look at the U.S. too. It's hard to see that there's actually some outside of Nevada and Alaska, one in Mississippi, for example, in the 60s.
Was that one installed?
That one wasn't solved, right? That was the test of the decoupling, which we'll talk about kind of later on in the talk. So if you want to monitor for these tests, you have to be prepared to look for them in all environments, right? They could happen in space, in the atmosphere, underground, underwater, on the surface. And there's other things that you're going to see if you're monitoring as well. Volcanoes, earthquakes, mine collapses, mine blasts, various sorts of other explosions that happen on the surface of the water. And so you're going to want to look for the products, radiation, shock waves, debris that are going to propagate some distance depending on the size and how you've done the explosion, how you contained it. But the general things that you want to use are underground testing, you want seismic waves. For underwater, you're going to look for hydroacoustics, so that's sound waves in the ocean. In air, you can look for acoustic signals for very prompt or faster travel times, or you can look for the radioactive debris, which takes longer to disperse. And in space, you're going to look for radiation, you look for direct radiation effects. And your treaties that we're going to talk about really depend upon these monitoring technologies. They're really impacted by how well you could use these kinds of signals to monitor for tests. We'll talk about that as we go through. So this is just kind of an overview of the treaties we'll talk about and some of the tests. So starting with the first one in 1945, the first nuclear test Trinity in New Mexico. The first underground test was in 1957. It was contained. That's called Rainier. That ability to contain these tests led to the so-called limited test ban treaty, which bans testing above ground. We'll talk about that. The Non-Proliferation Treaty was about keeping the spread of weapons contained to the 5 declared countries that had them. We'll talk about that. You can see that the last atmospheric test was in 1980, so that's part of the reason why there's so much emphasis on seismology for the monitoring, because most of the testing after, all the testing after 1980 is underground. And then you can see in 74, this threshold testing treaty that limits the size of testing was signed, principally by the US and the former Soviet Union at that time. And then as the nuclear power stopped testing, so the last US test was in 1992, the comprehensive testing treaty was signed in 96. And that led to the declared power stopping testing, and only the countries that have not signed the CTBT have tested since then. We'll talk about those too. All right, so you probably have read about this or heard about it, but obviously the first test coming out of the Manhattan Project was done in New Mexico, in this area here, on a tower. It was on the order of 20 KT. Released wasn't completed, so radionuclides were distributed. Interestingly, there were seismograms also generated from the earth shaking. The station here in Tucson. They gave paper on this in 1946. You look up and see the seismogram in it. Here's a device, a gadget as they call it, in the tower. You can see that immediately you start thinking about diagnostics for how you're going to identify what you're seeing and do analysis on the devices. That was a big part of testing, was doing the analysis on the devices and saying things about how big was it, how efficiently did it go, what can we learn from the tests. So after the war, well, a couple things to say. First, this 1945 test was an implosion tuning design, which is the same as the so-called back-end device that was used in Nagasaki in World War II. But something that is quite relevant to testing is that the uranium then design, the so-called Little Boy device, which was used in Hiroshima, didn't have a full test. They were confident enough that that was going to work. They didn't actually do a full-scale test before they dropped it. So that's something to keep in mind. If you're a proliferating country and you're building devices, you don't necessarily have to test them to know that they're going to work. It's a question of your confidence in your calculations and your design. So that's something that sometimes people forget about. The U.S. carried out a series of atmospheric tests starting in 1946 after the war. These famous ones at Bikini. This one, there's a bunch of, it's hard to see here, but there's old ships. They're not that old, but leftover ships from World War II that were put out here. They were looking at weapons effects tests. At the start of the end of World War II and the start of the Cold War, there was a lot of concern that there would actually be a nuclear war and weapons effects had to be studied and looked at. In addition, they were developing the devices to be more powerful than the first 20 kiloton device. So there was a series of atmospheric tests in 46 on. The first Soviet nuclear test happened in 1949, estimated to be about 20 kt, and its radioactive debris was detected by a U.S. Air Force plane that picked it up. This was a surprise, I think, to a number of countries. There were estimates that the Soviets weren't going to be able to have a nuclear weapon for several more years. So this concern, but it also answers the question as we go on here, why the Air Force does treaty monitoring from these days. Once the Soviets started testing both the U.S. and the Soviet Union, and in fact the United Kingdom carried out many nuclear tests in the 1950s, almost all atmospheric until the very end of the 1950s. UK did tests in Australia. An issue that you'll read about too is the fallout effects, right? So you're doing atmospheric tests. If they're not done high enough, then the fireball hits the ground, sucks up a lot of debris, and goes out into the world, causes problems. Yeah.
I was just wondering if the Air Force data collection, was that in Soviet airspace, you know, or?
I think it was not. I think it was in the Pacific, but
Yeah.
But it's been a while since I've read the details of that.
Oh, they tested in the Pacific.
No, I think the debris had originally debris to come across Asia and get out to international airspace.
I think they picked it up on some U2s.
That could be too, but this one is pre-U2 era. This is actually not that dissimilar to the plane that they still fly. As a matter of fact. Sort of weather reconnaissance plane. The Air Force has a lot of weather reconnaissance and stuff. So it's re-outfitted to collect debris. Debris and those able to be brought back to a lab and analyzed, see what was going on. So this fallout caused a lot of public protests. You can read in the era, there's this famous Castle Bravo test that contaminated a fishing boat, killed some people. There was radioactive fallout getting into milk and strontium and calcium. A lot of concern, strong public concern about this. And that was led to discussions for a moratorium. There was actually sort of discussions about a moratorium right from the end of World War II. A lot of different plans were put out. None of them really panned out. It was a fascinating history to read about that. But
The Kennedy JFK White House was picketed by large numbers of people demanding the cessation of testing.
Right.
On the grounds that strontium-90 was seeping into the milk that they were feeding their kids. And this was affecting Kennedy's attitude, which ultimately led to the women testimony.
Yeah. And I'll talk about that a little bit. Yeah. There was discussions between the countries going back to the end of World War II, but it really took a more concrete form in '58 when there was negotiations were opened up in Geneva between the U.S. and Soviet Union and the UK about the test ban. And the Soviets actually started a moratorium on nuclear testing, and the U.S. followed suit. So the Soviets started in '58, and the U.S. started in '59. Interestingly, and this is something I had kind of forgotten about while I was putting this stuff together, but French carried out their first nuclear test right in the middle of this moratorium in 1960 in Algeria. It probably very helpful to the discussions. And interestingly, too, it's not 20 kt like the U.S. and the Soviets, it's 70 kt. Yeah. So very interesting.
And this was, I forget, during the Algerian Civil War.
I think that happened right after that.
I'm gonna be right after that.
Yeah, and there was negotiations where the French retained some rights to the testing
in Algeria.
right? Which seems hard to believe today. But.
Right.
very, very interesting. But basically, there's a variety of Cold War pressures. There's the U-2 shot down in 1960. There's the Berlin Wall. There's the French test, which the Soviets said was as good as the U.S. test. All those things conspired to end the moratorium, first by Soviet Union in 61, then the U.S. Resumed testing in 62. And if you go back to that plot of the test, you'll see it resumed a pretty big spike in tests after that. Again, the combination of the public pressure and concern about fallout didn't abate, though. Came back when the moratorium ended. And one of the things I should have put a slide in here on, well, I guess it's coming up next, is when the U.S. first tested underground, it was kind of surprised by the signals it got. They were expecting to see something that looked very different from an earthquake, something that would be very easily distinguishable from an earthquake, and in fact, it looked an awful lot like an earthquake. And so immediately there were some technical issues that arose about how are we actually going to identify these explosions, underground explosions. So that led to a vigorous discussion in Geneva on the test ban. But the thing that the two sides could agree on was this limited test ban treaty in 1963. So this is a treaty that limits testing to below ground. So no atmospheric testing or space or underwater testing. And the specific language is here. You have the grid debris. It's not present outside of the territorial limits of the state under whose jurisdiction or control. This is interesting as a side note because the kind of detection levels that were available in the 60s is very, very different from now. You would be able to detect all kinds of things now that you could not detect in the 60s. So that makes this actually a very hard thing to meet if you were still testing on the ground as all the countries were. An interesting thing too is there's no specific verification regime established. So the treaty set up, they're like, well, we can't agree on a comprehensive test ban treaty. You have all these problems, but we can agree, well, we'll just test on the ground. That will solve our public relations problem. It contains the debris, which maybe they'll want the other side to see what you're doing. Solves a lot of issues. It's thought, well, we can verify this with our national technical means, which means things that each country controls. And could be agreed fairly quickly. So that was agreed to in 63. There's only 3 countries that are party to this agreement. So US, UK, Soviet Union. So the French tested minimal moratorium, not a party to this. Neither is China, neither is anything else. It's very interesting. There were some attempts actually to try and extend this to a comprehensive test ban treaty. That just was a non-starter from US and Soviet's perspective. So didn't happen.
So I think one other point that's embedded, it's embedded in here, I think I may have mentioned this briefly, was Kennedy was warned, this is after the Cuban Missile Crisis. Kennedy was terrified about the use of these weapons. He wanted to begin to move to some sort of control of nuclear weapons.
So did I.
And as they were completing this treaty, he was tipped off, Kennedy was tipped off, that the Joint Chiefs were going to oppose the treaty and testify against it in Senate hearings. And it turned out it was SAC that wanted, Strategic Air Command, that wanted to continue to have free reign on testing. So civilians in the Kennedy administration connected SAC, not that they needed to be connected, but connected them with the weapons lab scientists who reassured SAC that they could continue to modernize their nuclear weapons solely with underground testing. So that it actually was not such a big constraint on their weapons modernization. And that because of that, they would testify in support of the treaty. This is the reality of public policy in nuclear weapons.
Yeah, right. I mean, day-to-day, neither the US or the USSR was, no, that wasn't, their overriding concern was daily community tests. More than they wanted to do what was necessary to actually reach a testing and treatment agreement. So there was also a technical issue, which I mentioned, which was there wasn't really a good way to identify the explosions at the time in 63. The first results from the underground tests kind of surprised all the scientists. There were some expert panels that were put together. The expert panels said we need a vigorous research program, and we got to figure out what's going on with these underground tests, why they're looking so much like earthquakes, and how we're going to identify them. That led to a thing called the Available Uniform Program that actually produced some really nice results. By the mid-60s, you had one of these techniques. This is called MSNB. This is two different magnitude scales. This MS is a surface wave magnitude, so this is the surface wave part of the seismic. So we have an earthquake and explosion, kind of like I showed you at first. This part later in the wave train is the surface waves. And that, if you measure the amplitude of these, you get a magnitude for the events. It's set up so that for an earthquake, the MV and MS would give the same number, the same magnitude. But when you do it for an explosion, you get a pretty different number. So that, again, the MV part is measured on P wave. This is the fastest initial primary wave or sound wave traveling through the roof. So if you make a plot of MS versus MV, here's the earthquake in blue, here's the explosion in red, you have a pretty nice separation, although it's not perfect between the two. But one big problem is it's hard to make that measurement down at the small magnitudes. We'll get back to that. But when this was discovered in the 60s, it was a major breakthrough for a monitor. It made possible some of the later treaty negotiations that we'll talk about to go on.
Bill,
Yeah.
if I understand correctly, maybe we're going to get into technical parts later, the S wave and P wave propagate at different velocities, so the time difference actually is a distance indicator for triangulation. Okay.
That's right. And the surface waves travel at a different speed, a little bit slower.
Okay.
You can't really see in this plot the shear waves, but these are surface waves, so they're constrained to travel on the surface wave. So we'll come back to this. But this is one of these issues, one of the reasons why they couldn't, it's not clear if we had this before 63, if that would help or not, but it certainly was a reason why they couldn't agree in 63 to a more complete ban. All right, so that's this gap here. After the limited threshold testing, you can see that there's pretty vigorous testing going on underground. The French started testing underground in Algeria. China becomes the 5th nuclear power in 64 when it carries out its first nuclear test down at the sort of same 20-ish AT level. Very interestingly, India in 74 does an underground test for peaceful purposes. And it's estimated, there's actually a lot of controversy about what number this is, let's say, under 10 AT.
DNEs.
Right. But this is interesting because 74 is a ways after 68. And in 68, the Non-Proliferation Treaty was opened. So that's the treaty that said we're going to declare 5 nuclear weapon states, NWS here, US, Soviet Union, UK, France, China. And all the other signatories are non-nuclear weapon states. And under the obligations here, the nuclear weapon states can't transfer weapons or technology to the non-nuclear weapon states. So it's meant to constrain the proliferation of nuclear weapons. That's the stick. The carrot is that all the parties have the right to develop nuclear energy for peaceful purposes. So the happiness for peace idea that goes back to the 50s. This sets up a pretty interesting verification system. This establishes the International Atomic Energy Agency, the IAEA, that exists instead, and to monitor special nuclear materials or enriched materials, and can do inspections and all kinds of things to verify that the country is complying with these rules. So this is very interesting how it's set up at this time. But you can see India's not in here, and That's a problem that keeps coming back. Questions on this or comments?
No Israel, no Pakistan.
Yeah, no, that's right. So the next treaty was signed in '74. This is the threshold testing treaty. This one limits tests to no more than 150 kilotons. So this again gets to this idea that we're trying to limit the weapons, but we want to do something that is verifiable. And perhaps also plays into a role of how much you want to limit development by countries, how much they want to limit themselves. So it was thought that this would be fairly straightforward. 150 kilotons is pretty big. That's a magnitude 6-ish earthquake. Pretty easily detected anywhere in the world. There's not that many of them. Background events to look at. So and this time we have that MSMB experience. So it's thought to be fairly straightforward to monitor this treaty with national technical needs. So no special verification provisions set up. But if you notice this, it wasn't ratified until 1990. And the reason is that not immediately, but as time went on, there crept in problems about whether countries were, whether the Soviet Union in particular was obeying this treaty or not. And because there were differences in the amplitude of the seismic signals from the two test sites. So something that was as near the 150 kT limit by the US was about a magnitude 5.7, and something that was near the 150 kT limit by the Soviets was about 6.2. It's a log scale, so that fraction matters. It's like a factor of 3 in amplitude. So that's a little surprising if you're a geophysicist, though, that the geologies are extremely different between the two countries and the two test sites. That was in some sense predicted by the geophysicists, but not all of them. There was some controversy about that. And so this didn't really get resolved in order to get every satisfaction to be signed in 1990 until this very interesting experiment was done in 1988 called the Joint Verification Experiment. So this was negotiated during the Reagan administration. And what the US and the Soviet Union agreed to was to observe a nuclear test at each other's test sites and use hydrodynamic means. This is a very close-in measurement of shockwave growth at each other's test site as a way to verify how big the test was. And you can see, well, here's what I was mentioning about the differences in the seismic magnitude. I quoted the CPBT ads, which is slightly different. The difference is about the same, factor 3. But this was very intrusive. So I mean, this included U.S. and Soviet personnel at each other's test site, replacing devices, putting in hydrodynamic measurement tests, and measuring it. Seismic wasn't part of the official test because seismic was the one that was claiming that they weren't cheating. So it was in the outs. He was right. So after this test happened, it was shown that, in fact, there really is a geologic coupling difference between these two test sites. One's in a stable region, a region that hasn't had a lot of tectonic activity, very strong rock, vast rock. The other in Nevada is very active, mountains, weaker rock, slower velocity, so that affects how the amplitudes are generated. So this kind of proved it out. And it's really a remarkable test between the two countries. Maybe one of the high points of U.S. Soviet relations.
The question is, it begs a very intriguing point about intrusiveness, because whose weapon system do you choose, and how does the other side have confidence that the two are really identical, if you really do test with identical devices?
So each side was able to field their own hydrodynamics. So both were fielded at both tests. So the Soviets brought in their equipment to the U.S. The U.S. brought their equipment to the Soviet Union, not devices, but the hydrodynamics.
So each did their own device.
Each did their own. Each did their own device.
Yeah. Okay.
Supposed to be between 100 and 150 kT. And then each brought in their own hydrodynamic measurements and did their measurement tests. Just a side note, I was very fortunate. I was in grad school at the time And through private funding, was able to go to the Kazakhstan and record this test. And I can tell you personally, there's a very big difference in the happened because I was about 200 kilometers away from the Soviet test, and it was pretty good shape. There's no doubt that it happened. And then I was in the US, Nevada, about the same distance for the US test. I made a call in and said, it happened. Can't do it. So there's a pretty significant difference in the inside of it.
In the photo, which lab are the employees from?
I think they're a mix. Yeah, I don't have, I need to,
Los Alamos and Livermore?
I think it's Los Alamos and Livermore, yeah. I'm not sure if Sandia was really involved in Los Alamos and Livermore. I need to talk to my colleague Daisy that has more, probably potentially identify some of the people for you. Like I said, I was grad student, out in the fields at the time. Unofficial, no official relationship deal with so that really resolved the issue, and after that, this protocol was put in, which provides our hand-to-hand test measurements on tests over 50 kP. So this is very interesting too. So after this treaty was signed, if the U.S. and Soviet Union was going to do a test greater than 50 kP, they're supposed to notify the other side, and then the other side could bring in hydrodynamic measurements. Now, very interestingly, Soviets stopped testing in 1990. And in fact, Soviet Union ceased to exist very shortly after that. So this has never been exercised after the JDE test. But it's still on the books. If testing was resumed, of course, who knows how this will be observed, but it's still there.
But your assessment is that the U.S. at this time had substantial confidence that they could detect Soviet underground tests greater than 150 kT?
Yeah, that's right. Or even well less than that. The issue was not so much the detection and identification that, yeah, that was a nuclear test. It was how big was it. So it really came down to a yield estimation problem.
And
So
the error bar around the yield was pretty tight.
So we'll talk about that. The error bar, after this calibration, then it became tight. That's right. But before that, it became how you're factoring in the geology into your error bar. And that was really the problem. And so I actually have a nice little cartoon here. This is what a magnitude, size of magnitude versus yield formula looks like. They tend to be linear. But they're different. They're offset from each other depending on whether you're in a stable region or a tectonic region. So that's this 4/10 difference that was the cause of the problem for the US-Soviet Union case. But you actually have bigger potential problems because you can have so-called low coupling. This is like in alluvium. That's why we have that dry alluvium geology definition that I'll get to eventually. And you could have decoupling. So we'll talk about that too, but you could have the explosion occur in a large cavity. Then you reduce the altitude very significantly. So all of these things lead to yield differences that can be quite substantial. Actually, decoupling is a factor of 70. So that's huge. Yeah.
In one of your previous slides, you showed the difference between the earthquakes and the bomb. If you put it in a cavity and you shape the cavity with different metals, and because these are linear, can I shape like I can turn like a disturbance into a sinusoidal peak by just shaping the cavity like a.
This is a very interesting question. Yeah. There's been a lot of discussion about that, and people have done, synthetic analyses and things like that to look at, what could you do things to a cavity to either more muffle it or make it look more like an earthquake. So the U.S. actually did an experiment of decoupling in the 60s. That's the one in Mississippi and salt. So they excavated they originally wanted to excavate a salt dome, but that proved to be too hard. So they set up a nuclear test that created a cavity, and then they put, after a couple of years, they put another small device in the middle of that cavity and set it off, and came up and showed this factor of 70 difference. But that was a relatively circular test. And Russian Soviets did something very similar in salt domes in their country. But nobody really looked at oddball shapes and things. But that has been, if you look at the literature, there's a lot of discussion about that. And it's maybe a research question. What could you do? But we'll get to that too, because there's other problems, because you have to build a cavity big enough to decouple the test. That, I'll talk about that, but it needs to be pretty darn big, actually, for any test of any size. You've got to do that undetected. You've got to keep it intact. If it collapses, you can potentially see that. And you've got to keep all the radioactive materials in there too. If they get out, you'll be detected. So actually carrying out a decoupling test is technically quite challenging, especially if you want to do something large. And that was one of the conclusions of the National Cavity Study. So I'll mention that in a few slides. It's interesting. So the other thing I want to mention is, in addition to this sort of coupling, there's this issue about what goes on in the upper mantle of the Earth and whether you have more attenuation in some regions than other regions. That has to do with the tectonics of the Earth again. Let's go on here to the thinking about the testing treaty itself. So I think I mentioned in the beginning that the CTBT negotiations started in '58. Here's the picture. Essentially, some, if you look carefully here, there's very well-known people in these pictures. Some famous nuclear scientists. In this one, there's people like Hansby and others that are in there, part of the negotiations in the late 50s. And these things went on and off, all the way until '96. The negotiations moved to the Conference on Disarmament in Geneva. This is the Conference on Disarmament. And in 1996, the Conference Participant Treaty was moved to the UN for a vote and passed and went into effect. And what happened leading up to that was really both the technical capabilities for monitoring improved very significantly, so you can monitor down to very low sizes with confidence. And the 5 nuclear weapon countries basically stopped testing. So you had Russia stop in 1990 for political reasons. The US stopped in '92, France, UK, China in '96. So by the time the treaty signed, none of the nuclear weapon states are testing anymore. All are saying we're done, we're not testing anymore. So that really made it possible to have a CDB. But then you have 3 non-signatory countries that tested since then: India, Pakistan, and China, and then North Korea. Something like that. So let me take a little bit about the CTBT. This is a much more complicated treaty than the other ones. This one first sets up a very difficult entry to force requirement. 44 specific countries that have nuclear reactors, there's a list in the treaty, have to ratify before we enter into force. This includes some countries that wouldn't even sign the treaty, like India and Pakistan and North Korea, which, well, you can sign and not sign. You have countries that have signed, like the US and China, that have not ratified. So we'll talk a little bit about the US's ratification. China's position is it's a ratification that the US does. Leading it to the US. But you have some other difficult countries here too: Israel, Iran, Egypt, in the list. Here it's all nuclear explosion, so it's zero yield treaty. You don't need to be a scientist to realize that, obviously at some level, you can't monitor, firecracker size explosion at any distance. So there's some level at which you can't monitor zero yield treaty. So you get into these issues of you either have to negotiate some sort of a very low yield treaty, very low, that it's prohibiting anything you may call militarily significant. But then you get into all those issues we talked about the threshold test. How you know that's the right yield? How would you intrusively monitor that? So they agreed on a zero yield. But there's, of course, some sort of limit in practice. It depends on how vigorous your monitoring regime is, what that limit is. It establishes a test entry organization in Vienna and a verification regime. So this international monitoring system, I'll show you a map in a minute, of stations that are sending data back to Vienna. There's an on-site inspection. So this is something that had been argued about from the very earliest days. No one agree on it in those early days, but this establishes that it's limited to 1,000 square kilometers. But if a suspicious event happens, a team could be called up to go in and investigate that. And then there's some consultation, clarification, and confidence building. So much more elaborate verification regime than any of the previous treaties set up. Here's the International Monitoring System. 4 technologies. So it goes back to the first slide I was showing you on seismic from the ground, hydroacoustic for the oceans, infrasound for the atmosphere, and radionuclide for atmosphere and leaking out of the ground or out of the ocean. When this treaty was first signed in '96, this hardly existed. Each country put in specific stations or specific locations, but they had to be built out. So that's actually been a lot of the work in the last 20 years, is building out this system. It's now about approaching 90% complete. It's down to the very difficult cases that are just either logistically or politically or both difficult to get the stations in. Yeah.
Which countries are the biggest financial supporters to CTBTO?
Yeah, so it follows the UN rules. So it goes by GDP. So the US is the largest contributor, about 23%. And after that, it goes down, Germany and Japan are significant contributors. So it follows the GDP.
But US doesn't ratify.
US does not ratify. That's right. Yeah, so we're a very interesting state. I mean, we'll get to this, but the US was the first country to sign the CTBT in '96. And as we've seen in the threshold test ban treaty, and you can ratify a treaty and not, or you can sign a treaty and observe it, but not ratify for a year. So I mean, that's what's been happening in CTBT.
So I was in the Arms Control Agency in the Clinton administration when Clinton put forward the CTBT Senate ratification. And of course, it's a complex, very political process. The Republicans had a majority in the Senate at the time, and Clinton assigned Senator Biden to build support among the Republicans and the Democrats to ratify the CTBT, and he failed miserably. It barely had a majority vote, it needed 2/3 vote in the Senate. I think it had like 53, may have even had fewer votes than half.
Yeah.
But it was a disastrous lack of ratification, and then under George W. Bush, he was not particularly interested in it, so there wasn't any activity there. But then under Obama, I was back in again, Obama was interested in it, but they did a real nose count of the Senate and said it's hopeless, there's no way. And the principal objection was, at least professed principal objection, was lack of confidence in the ability to detect very low yield Russian nuclear tests. And they said, if we can't have confidence in those, we're not going to sign the treaty. And it's been stuck ever since 1998 to today. So we are a signator, but not a member. We've never ratified.
I've got a slide on this. In '99, this debate, and
Okay, sorry.
well, this was a big deal. It got very politicized because the Democrats were threatening to oppose the legislation. They're kind of taunting the Republicans, not a smart idea. CTBT moved it. The Republicans called their bluff, moved to the floor for a quick vote. And as was mentioned, you need 67, you need 2/3 ratification. It had a bare majority.
51-48, so it didn't even get a majority of senators.
And all those things were cited: lack of verifiability, nuclear stockpile safety, integrity, unreliability, zero yield, lack of non-proliferation value were cited. And couple things at the time, though, was that the U.S. Stockpile Stewardship Program and the International Monitoring System were both pretty new, not really very tested. They're now more mature. So there are Republicans like George Shultz who said, you might have been right to vote against it in '99, and you might be right to vote for it now. Because things have changed, but that is not widespread, right? Not widespread
No.
view at present. I was looking at this, to see how many senators are left. There's 16 the senators that were around in 99 are still in the Senate. So evenly divided. But, very interestingly, this is from the most recent nuclear posture review. So this is the document that is put together every few years, usually by a new administration, to say, well, this is what our nuclear policy is going to be. You can see they're not going to seek ratification of the CPTPP, but they're going to support the CPTO and the International Monitoring System and the International Data Center. And they're not going to resume nuclear testing unless necessary.
Right.
So we were in this weird limbo state for a while. Obama wanted to ratify, but the Senate wasn't there. George W. and current administration don't want to ratify, but we're in this weird, sign and observing, but not ratified state. And that could go on for a while, or potentially countries could say, you're getting all the benefits of this and you're not living up to the treaty and things will start to fall apart. We don't know how this is going to play out.
I think this was actually much more moderate language from the Trump administration than critics and skeptics of the Trump administration expected.
Yeah.
They thought they'd pull out of support for the monitoring system in the data center, or Trump would say, let's resume nuclear testing.
Right.
He didn't do any of that.
Of course, this is prior to John Bolton having joined the administration.
That's right.
John Bolton is a vehement non-supporter of the treaty.
Right, that's right.
Not just a fundamental.
And Mattis was still Secretary of Defense, who was much more moderate.
So, stay tuned.
Exactly.
I can't remember if I remember this correctly, but isn't there like a presidential order of some sort that does prevent the U.S. from testing? I mean, obviously, the president can withdraw other presidents.
So it's true that testing stopped when George H.W. Bush basically said, no more testing.
Right.
So it started with a moratorium in 1980. So that was the U.S. We're just not going to test anymore. The declaration prior to the CE. So, yeah, that could be unmet.
But so we currently have facilities to test our weapon systems without being considered a nuclear test. But when going back to doing a full-scale nuclear test and recreating some of those facilities and, some of the instrumentation stuff take a very long time to do?
Well, so this is a very interesting question too.
Yeah, I don't know
So
if
the
you can say
US,
how quickly it would take to suddenly turn some of that and actually perform a test.
that's all true. Although the US has a test readiness program. So when testing ceased, there were a set of conditions that were put in place that were necessary for ratification, and one of them was a readiness program. So that if the U.S., so the treaty has a supreme interest withdrawal clause. So any country can say with 6 months notification that, hey, we have to test for whatever the reason is. We're going to withdraw from the treaty and conduct a test. And so as part of that, so the U.S. had a stockpile stewardship program to say our stockpile is robust and secure. So there's no, treaty doesn't affect the actual stockpile that's used for deterrence. So the U.S. said, if we did have to do that, we're going to have a test readiness program. We're going to maintain some capabilities at the test site to be able to resume testing within some time period. That number has been changed over the years, but it's always on the order of 18 months to 36 months, something like that. So yes, you're right, but the U.S. is trying to keep some things going at the test site in case they did have to resume testing. So I think there were some things that maybe I don't need to go too much into them, but I wanted to say a couple things. So first, this data goes to Vienna, and from Vienna it goes to each country's national data center. And I mentioned earlier the Air Force is the U.S. National Data Center. It's actually the Air Force technical applications that are at that does that. So that the data goes to them, to other countries' national data centers. They're the ones that do the 24/7 monitoring. One thing that came out of these National Academy studies were mentioned is you actually have several systems to monitor, right? You always have national technical. So that can focus on areas of interest in different countries. So if countries concerned about their neighbor or their competitor, they can take extra steps to monitor them. You've got this international monitoring system, which is every country kind of a baseline of what can be done. And then you have existing sensor networks that are run for other purposes. For example, there's a lot of seismometers in the world that are out there working. You could use to monitor if a question comes up. So the capabilities are actually better than just the international monitoring system. And this is really changing. I mean, we all have seismometers in our cell phones now. Of course, they're not very good, but they're getting better. There's seismometers in all kinds of things now. So the question is, how do you use that? Could you use that? Right now, cell phones aren't going to help you. I'll tell you that right now because they're so bad. It being closer doesn't, you have to be so much closer that it doesn't help. But there's lots of other systems out there that might be useful. And as time goes on, that's going to change. I wanted to show you a couple of things. So this is a very famous picture. This is from the 1988 Office of Technology Assessment Report. How big of a cavity do you need to decouple a nuclear test? So for 5 kilotons, which is on the small side, remember the first nuclear test running with 20 kT, you need a cavity that can contain the stature limit. It's going to be 43 meters radius. It's pretty big. So constructing that, carrying out the test, keeping it intact, keeping nothing leaking out of it is challenging. That's kind of why in this National Academy report, actually, I happen to leave a copy here for you guys. It's actually a great reference. Highly recommend it. It's got a lot of good history and interesting things in it. If you look at this table, basically, you're not going to be able to conduct a test that's much bigger than a few kilotons. In fact, this book would argue you have to do less than a kiloton test to be able to do it decoupled. So that's pretty small. It's tough to do. So this goes into various technical things about why you might test, and it separates countries of lesser experience and countries with more experience. But it's fascinating. It's actually amazing that this is much detailed out. So there's a huge amount of detail there. If you're interested in all this topic, I'd recommend looking at that. You can get the PDF for free from the National Academy. Just go there, download it. Okay. All right, technical. So we won't have too much time to get into this, but I'll try and hit a couple of high points on this. So one thing is, what do scientists that do nuclear explosive monitoring actually do? And it turns out there's quite a lot. There's a very long history of R&D to improve nuclear test monitoring that we talked about going all the way back to the 50s. It's ongoing today, so there's R&D right now. There's also experts, so delegates to treaty negotiations. So Jay Zuka is one of my colleagues. He was a negotiator on CTBT. Support for these preparatory activities. So there's a lot of all the details that are not in the treaty, like how is the International Data Center going to process the seismic data, make magnitude estimates, make measurements, and send them out. All those details are worked out by what's called Working Group B. Working Group A is the financial group. Working Group B is the technical group. So this is a group that meets in Vienna twice a year. All the countries that sign, plus others that want to be there as observers, can be there. It's full translation. You go there in 5 languages in the US, so there's constant discussions of all these very fine points. I'd say that it's there's a lot more lawyers than technical people than I've been to a few of these, and there's a lot of arguing over words in language. Language matters a lot, but gradually over years, things have been hammered out, so there's a smooth way to process the data and send it out to each country and do the process. A lot of work is going on. There's serving on-site inspectors, so until the treaty enters in force, we can't do an on-site inspection, but they actually have picked technical people, trained them, done exercises, big field-scale exercises with those inspectors. We have a few at the lab. do that. And there's about 35 people in our group, our group from last year, that are involved in this. So there's a lot of really interesting science to be done. That's my one advertisement slide. Why you should become a nuclear running scientist. Okay, go back to this. So we brought this up a couple times. It's hard to tell, you know, an explosion, like an underground explosion from all this background stuff. And these tests that have happened since the test ban was signed offer a way to kind of check how are we doing. So I want to talk a little bit about that. I'll just mention too that if you were a national data center and you have a treaty monitoring mission, it's an operational kind of mission. That's not unlike what the USGS does for earthquakes. You're going to bring in data, you're going to detect something in the signals, you're going to locate it, identify it. If you think it's an explosion, you're going to do a yield estimation. You're going to put it in some sort of context. Is this the first test or the nth test in a region? And you're going to notify national authorities that something is happening. They have to do this over, they have guidelines of how they do that, but it's very strict set of rules they have to follow to do that. So they need good algorithms and calibration products to run through this process. Very interesting. I got to be at the U.S. National Data Center back in '96 for one of the Chinese tests. It's very, very interesting to see how this is done. And you're doing something in a hurry, you really can't be, you know, sitting back and thinking, well, I have the test, and with that, you're going to have everything ready to go. Very, very interesting.
You probably can't comment, but I'm wondering how fast you need to do it.
I can't.
For earthquake seismology, it's, you know, we've always been trying to reduce the time.
That's right.
Down to a few minutes after the earthquake.
And that's
a lot of time.
I mean, it's not different for this problem too. But the consequences of being wrong are greater, so you really gotta know what you're doing. I want to mention there's sort of two general scenarios for nuclear test monitoring. So this is kind of a cartoon, but you might have a map with some, here's some stations, here's your first event in a region. You've got to have pre-calibrated everything if you're going to be fighting that event. Needle in the haystack problem and saying, yeah, that's an explosion, and a nuclear explosion, then you worry about it. If you have a test site which has had previous tests, then there's some very interesting things you can do if another test happens. You can look at relative timing and amplitudes and things between those tests to get very accurate information. So this is in some sense an easier case, and this is where we've been for the North Korean tests the last 13 years. So let me show you, I'll walk you through kind of how you do this for the last North Korean test that happened in 2017. So I'll talk a little bit about detection location. Discrimination is a jargon word for identifying explosions in the background signals. These are statistical term, you discriminate it from other events, and then yield estimation. So the 2017 test is big. It's over a magnitude 6 event. It's the biggest test in many tens of years. So it's quite a large test. There's no doubt what happened. I was actually dropping my daughter off at college at the time this happened. Got an alert on my phone because that's where you get alerts these days. USGS. So I see magnitude 5.2 North Korea. Piques my interest. Very interesting. 15 minutes later, it's updated to 6.3. Very, very interesting. My colleagues from Norway had a very famous tweet when that happened. And USGS had this map right away. See, okay, this is near where the test site is. It's big. Looks like it could be an nuclear test. I love this too. The USGS says this, you feel it report. So if you feel an earthquake, you can report that, and they take that in. There's some reports from North Korea and China. This being done. But it was like 3 hours before the North Koreans actually declared they had gotten a test. One of the reasons why you knew right away what it was is if you compare the tests. So here's a station in China, about 350 kilometers away, This is the telemetry station, so you can bring the data in near real time. And here's the first 5 tests, and then here's the one that happens September 2017. You can see it's very, very similar looking. That doesn't happen unless it's a similar mechanism and a similar location. So right away, this is going to be test. But this is scaled, self-scaled. Here's what the axis is. It's 10 times bigger than the previous ones. Very interesting. We can actually use the relative timing of these different phases. This is the PN and PG, S, the LG phase, the surface waves to get really nice relative location. You can get the pattern of where these tests are by their relative timing to meters. This is actually the uncertainty ellipses. So think of this pattern of 5 tests here as being extremely well constrained, but where they're located on the map is not so well constrained. That's the absolute. What my colleague Steve Myers did is they used an INSAR signal here, some substance that appears to be related to this January 2016 test, to pin this one down. When they pin that one down, then that puts all these others in place. You can see that the September one is under the highest part of the mountain, which makes sense. It would be a very large test. You need a lot of overburden to contain that. So you can do remarkable things with these precision kinds of techniques now. If you didn't have INSAR, though, if it was the first test in a new region, then you're going to triangulate. So I think, as Carl mentioned, you could use the time difference between the P waves and the S waves to get an approximate distance, and you could use different stations to triangulate and locate the event. The problem is the Earth isn't homogeneous, though, so it's got this structure in it. These red regions are slow, the blue regions are fast relative to the average. This is because of plate tectonics and things moving around in the mantle and mantle dynamics. So you need a good model. So that's one of the things we do too, develop good models of the Earth, use that to improve our locations. Our goal is to try to get absolute locations down to 5 kilometers, which is quite good. I think 10 years ago or 15 years ago, we were at 20 kilometers. So it's been a big improvement too. And then you have to identify. So that MSMD technique I told you about worked great, but the first Earth gradient test, it had this so-called screening line. This is the line where you're saying everything on this side of the line is an earthquake, and I don't have to worry about it. Whoops. Problem. Bit of a surprise for everybody if that happens. So this technique has been subject to a lot of research to try and understand it. I would say the jury is still out, but there's some good plausible hypotheses about why this is happening. But it shows us that you can be surprised when you test under different conditions in different regions of the world. Fortunately, there was another method, the so-called P-S ratio. So this is P waves. These are S waves in the called LG. This is a nomenclature artifact, but these are S waves. You can see here's an earthquake in South Korea. Here's that nuclear test. Huge S waves here, very little here. That's a diagnostic signal. So this is another discriminant that we use to identify events. And if I show you the 6 tests, this is that ratio of P to S versus time here. There's all the nuclear tests here. Here's a background of earthquakes in and around the region, all around here. So they separate out nicely. We have other ways to identify tests that were developed in the 90s that work very nicely, which is good. So now if I go back, what I showed you before with these 2 events, I'm going to show you 3 events. You know this one is the nuclear test because this is another earthquake. But the question is, how do you identify which one is a nuclear test of this? And the short answer is you calibrate. So this event and this event are down here, coordinate this station. So this is India. Here, this is Pakistan. The station's in Pakistan. This is an earthquake up here in Kyrgyzstan, here. And what we've done is taken all of the earthquakes that occur in and around this area and mapped out how strongly the waves die off as they propagate. So if the waves stay strong, we would call that low attenuation or high Q. The opposite, then there would be strong attenuation and low Q. So this is a map of that cube. It's a map of strong attenuation in red, weak attenuation in purple. So these two events here, this earthquake and this nuclear test, have almost no change if they propagate to this station. But this earthquake up here gets its S waves wiped out. It probably looked like that, would look like that if it wasn't attenuated. But this filters it into this. Wow, that nuclear test. So if you take that PS ratio over here versus distance, just raw, mix them all together, you have a big jumbled mess. Apply this set of corrections to it, and just one pops out very nicely. So this is the kind of calibration that's done ahead of time, so that if you're there in the middle of the night, and you know what's going on, you can apply these things and have confidence in them. Almost out of time, I guess. Let me just show you one other. I'm going to jump ahead. Too much stuff here. I'm going to show you one last thing. So you might say, well, what's left to do? Given that we have all these very nice techniques. And one of the things left to do is we look at the depth of burial versus the size. This is the magnitude scale. Most of the nuclear tests were done in this sort of scale depth range. It was kind of narrow. But basically, you didn't want to drill any deeper than you had to. You wanted to drill deep enough that it was contained, but not any deeper than that, because it costs money to do that. So pretty much tested in here, and all of our empirical data is in this kind of range. If you're a vader and you want to do a test and you want everybody to know, you might want to go deeper than that. You want to go quite deep because you don't want anything to get out. You don't get any chance of getting out. So then you might be in this shaded region here where there's just not very much data. And the little bit of data we do have is a little concerning. So this is a case of the PS ratio. So here's your nuclear tests in red. These are Russian nuclear tests and Chinese nuclear tests. Here's earthquakes here in blue at a station in Kazakhstan. Here's a super deep, 2.1 kilometers deep PNE that was done in 81. And it's falling in the middle of the earthquake population. Why is that? You don't really understand that very well. So we're trying to do some experiments now with chemical explosions to better understand how explosions generate these shear waves and how they do it as a function of depth and the material we're doing. So this is some current things that we've been doing at the test site. We went up here to the northern part of the test site in granite and did 6 chemical explosions in the same borehole recorded on a common network. So we can cancel out effects, just look at what these depth and size effects are. And now we're doing the same thing in the Ludium hole. War tests, we've done 2 of these so far. But in luck, we'll do the next one in a few weeks, I hope, and then the 4th one by the summer. And that data is actually made publicly available through IRIS, and people that are interested in looking at that, data is available. So we're trying to understand this generation of the shear waves and understand that effect that I was showing you, and see if we can, understand and map that out over time. So I think that's probably a good place to start. There's other things I could show you. I'll just say one last thing is that we're trying very hard to move toward a scientific basis for monitoring. So instead of doing it empirically, where we have all the test data, like the North Korean tests or the Chinese tests or our own tests, can we do this in first principles? Can we put an explosion in a medium, simulate the explosion, simulate the interaction with the medium? It gets complicated. We can simulate the joints in granite, so those are planes of weakness. Granite is molten rock and placed underground. When it cools, it cracks preferential planes. You set up the explosion in that, those planes are driven by little earthquakes and generate shear waves. You've got to put in a hydrodynamic regime, so this is where you've got nonlinear effects going on, and you've got the surface bulging up. And then you've got to couple that into the elastic regime and carry it out to your stations. So we've developed all this machinery to do this, and we're in the process of kind of testing and verifying it with both historic nuclear data and these chemical explosions in it. We're trying to do this in a way that in the future you could just say, if I had a hypothetical test here and a hypothetical monitoring system there, what can I do? That's kind of the goal we're driving towards. So with that,
great. Questions, comments, criticism?
Take questions. conference going on for
Maybe this is a silly question.
No silly questions.
So based on your some technical expertise and networks with other scholars in the world, so can you estimate how many countries have the technologies for clandestine nuclear tests?
Well, that's a tricky question. Well, let's put it this way: the CTBT, if you forced, put every country that has a nuclear reactor that they had to stop. So, in some sense, the idea was if you have nuclear reactor technology, you know something about processing and operating special nuclear materials. So, maybe that's the easiest way to answer your question. And that would be a wide, that's 44 countries, that's a lot of countries. You know, on the other hand, there's only 5 recognized nuclear weapon countries plus the 3 that are not recognized that have tested. Or declared tested.
Thank you.
Yeah.
Yeah. Are there, for instance, codes that exist where you put in a suspicious time series, explosion, or certain confidence?
Right.
Does that exist?
Well, that's one of the things we try to do is develop that confidence level. So we develop physical models for the, or something like, say, the PDAS ratio, or that we would do statistical. We did do simulations via things like I showed you, or we have enough data, we'd love to do it empirically. We develop a confidence interval and then develop some kind of statistics of what your overall discrimination capability is. So it's not an easy thing. There's quite a bit of judgment in sort of determining what that is. Yeah.
Physics Today had, I find it, I'll put it up on the eCourse site. 5 years ago, they had a wonderful article talking about the global network of 100 and something, and then they had 10 or 11 hyperacoustic stations.
Yes.
And the thing that amazed me, I couldn't believe it even to this day. Apparently the transmission through water is so good that no matter where you are in the world, if anybody set off a 10-pound stick of dynamite, you could hear it anywhere.
That's right.
And I was astonished that it's that good. So that's not a place you want to do to hide a nuclear weapon.
Yeah, it is fascinating because you only have 11 hydroacoustic stations to cover most of the world's oceans with it. And it turns out that it's a little bit like a fiber optic cable. You have the velocity goes in such a way that it traps the waves in the SOFAR channel,
Yes.
Sounding and ranging channel. And so you can hear, I mean, they can pick up like dynamite fishing, people, which is not a good thing, but people in some countries throw dynamite in and kill fish and then collect them that way. You can pick those up across the ocean. It's remarkable. But if your test happens not in the SOFAR channel, then that doesn't work as well.
Okay.
Yeah.
If you surround your test with a lot of water and it's still underground, it shouldn't. But won't that reduce the magnitude?
Actually, no, it turns out, so water turns out to be an excellent coupling device. So if you test in water, it couples extremely well. It's incompressible. So it couples extremely well the seismic energy. So you actually get enhanced coupling if you shoot in water. Very interesting. And the Soviets actually did some tests where they had cavities from past nuclear tests that were water filled, and then they did some shots in them, and you can see enhanced coupling.
I see. But you have to go through these phase changes, or you have to put more energy into phase changes.
Well, that is true. So I mean, yes, it does get more complicated because you're going to evaporate that water, maybe turn into plasma, some of it. So it's more complicated. But the initial result is that you actually get stronger seismic signal after you detonate the water. So detonating a big empty cavity turns out to be better, much better, if you want to reduce the effort.
Okay, we're about out of time. Last thoughts? Let's thank our speaker very much.
Thank you.
This will be back in order.